Hello, physics students. So we just finished our first topic, the electrostatics of point charges. In that topic, we were looking at situations where we had just little points of charge, like protons or electrons, arrayed in space in some kind of configuration. And then we found the force among those charges, maybe the electric field caused by those charges, the potential energy, electrical potential energy of those charges, and the electric potential or voltage. Again, just point charges. But what we're moving on to now is what I call distributed charge. What I mean by that is we have more than just little nuggets of charge. We have countless millions, billions, moles of electrons or extra protons that are smeared throughout an object. And now we want to find the electric field caused by that charge, that even though it's little nuggets of electrons possibly along a surface or along a line or through a volume, because there's so many, we think of it as evenly smeared out along a surface. And now, so maybe we want to find the electric field caused by a bar of charge at a point. We cannot use the formula kq over r squared directly, because that formula applies to a single dot and the electric field around it. So that's what we're going to do in this topic, is learn techniques for how to find the electric field for charge spread out over objects. So you could spread it, as I mentioned, along a line like this, or you could spread charge over a surface like a piece of paper, or maybe over the surface of a sphere or cylinder, but along a surface. Or you could spread charge in a volume, like in this block of wood. Maybe inside every single cell, I add an extra electron or remove one electron, so it's spread all throughout the volume. So, in order to proceed, first we've got to quantify how concentrated that charge is. So that's what we're going to do first. We're going to learn how to calculate charge densities. I'll step aside here. You could jot this down, the charge densities for a line of charge and along a surface. Okay, so again, I'm smearing charge, either adding electrons or removing electrons, so this bar is positive or negative. It has a certain net charge then, and a certain length. Then we can find the charge density. This is a Greek letter, linear charge density, how concentrated the charges are in a given meter, by taking the total charge over the total length, and then the answer there is the charge density in coulombs per meter. Okay? Or we could take the charge and smear it along, like, say, a piece of paper. So now we're spreading it in 2 dimensions. So here's my 2-dimensional surface. By the way, now we're going to be moving on to, spreading charge out. And so it's a good skill to have to be able to draw 3D shapes on a 2D surface. It sometimes helps the problem solving in physics, because we are going to be talking about multiple dimensions. So notice here, I like to do this. I have a lot of fun with it. I made this letter A appear as if it's laying on the surface. If you like doing that, I'll tell you the secret. Okay, so what you could do is you can imagine a grid on this surface, right? So here's a grid, like a graph paper. And now if you want to draw a letter A, you start and end here, and then at the midpoint here is the top of the A, and then you come down like this. And then the horizontal segment of the letter A has to be parallel to these lines, like that. So, or you could do the letter B or C, whatever. You just imagine that grid, and then you try and fit the letter into it. Okay, so kind of fun, but not really that critical. So there's a certain charge in a certain area here. I'm spreading the charge along. And then the charge density, we need a new symbol. So we use another letter from the Greek alphabet, not lambda, but sigma. Sigma is like an O with a line going across, as you can see. And it's defined as the charge over area The units of that are in coulombs per meter squared. And then you also have to remember when calculating these charge densities that you have to be able to calculate the area of a rectangle or a circle if the charge is spread over a circle, or a sphere. If you take like charge and you spread it on the outside of a basketball, then the area that the charge is spread over is 4 pi r squared, the surface area of a sphere. Or if you have a cylinder, well, I guess I got a cylinder here, right? So on the outside here, then it's 2 pi RL. And the way we figure that out is if I have this cylinder and I take this surface, spread charge along it, and I want the area of that, if I take that and cut this and open it up, then the cylinder becomes a rectangle. And the cylinder had one dimension, which was this, which was the circumference of a circle, 2 pi r. And then the length of the cylinder is the other dimension. So see 2 pi r here, L over here. So it's length times width, essentially. That's what that formula is, okay? So different charge densities. Final charge density is if I spread the charge over a volume, then I drew a little cube here. I got a certain charge that's spread all throughout that volume. We need another Greek letter. We use the symbol rho. It goes like this, okay? That's how you draw rho. And it's defined as the charge divided by the volume, how packed in the coulombs are in the meters cubed, okay? So it's kind of like mass density, grams per cc cubic centimeter. Well, this is coulombs per cubic meter. And then you also need to remember these formulas. Volume of a cube, sometimes you'll need that in your calculations. The volume of a cylinder is the area of the base of it, pi r squared, times the height. And the volume of a sphere, 4/3 pi r cubed. Okay, so these are the definitions of charge density. Now, we're going to use these. Our first example of distributed charge, calculating the electric field for this situation. So, oops. Oops. All right, so we've got a charge that's spread along a line, and then that line is bent into an arc like this, okay? And we want to find, first of all, the lambda, the charge density along this arc, and then the electric field at the center point. So like right here at the center of curvature, okay? If this were like a circle, it's where the radii vector meets the center of the circle. So let me sketch that. Actually, yeah, maybe I'll do that here. So, by the way, 2 pi over 3 is 120 degrees. So it's about a third of a circle. So we want to know the electric field at that point. This is radius r, and so that's the part B. Part A, though, the lambda, the charge per unit length, we would find that by saying lambda is always the q over the length. Now we know that the arc has a charge of plus q, but what is the length of that arc? Well, it's the arc length, which is r times theta. From mechanics, when we studied rotation, that's the arc length of the length of a particular arc. So in our case, our theta is 2 pi over 3. Okay. By the way, this is just a general expression of the circumference of a circle. A circumference of a circle is r times 2 pi, right? That's all the way around a circle. Well, for a part of a circle, you just put the angle other than 2 pi, the whole angle around a circle. So that comes out to be, flipping the 3 to the top, there is the charge density. Okay, I'll pause the video to give you an opportunity to jot this down. Okay, now part B, finding the electric field caused by this arc at this point right here. So we can't use kq over r squared for this entire arc because it only works for a dot of charge and finding the electric field around that. But that's the only formula we have for electric field. So we can actually use it as long as we imagine a little part of this arc that can act like a proton. So maybe somewhere around here, I'm going to slice away a little bit of charge here. And it's really small. So small you can't even see it, so it looks like a proton. But I'm drawing it bigger so that you could see it. That has a little fragment of q. So just like when we have a fragment of x, we could say dx is like a little piece of x. This is going to be dq, a little piece of charge. And then that little bit creates an electric field here because it's positive, pointing directly away. Like this, dE. That lined up? Well, close enough, I suppose. So now we can use kq over r squared for that piece to accurately get the length of this arrow. But we don't want just the electric field caused by that one piece. We want it for the whole arc. So what we have to now do is add up the little bits of electric field for all pieces of this arc, starting here and ending here. And as we do that, you could see that at some point, as we're adding up those little pieces, we'll end up here, adding the piece of this electric field to the piece of electric field here, and this will create an electric field that points like this. And what you could see, if it points like this, it has the same vertical component up as this has a vertical component down. So as we're adding up all these pieces, ultimately the vertical components will cancel. The only parts that survive are in the x direction. So we can say that in the end, what we're interested in is only adding up the contributions going in the x direction. dEx, that will be the dE that I have here times the appropriate trig function. And if I put theta here, then I can say that I multiply that dE by cos theta to pick the x part, the only part that will survive that summation. Now, to find the total then, we're adding up, and of course, you know what the term I'm about to say. Adding up all these little bits is integration. So we're going to integrate, and I'm going to hold off on the limits just yet, dE K. Now, the dq, I want to fill in a little bit more. So remember I said that lambda equals q over L. So q equals lambda times L, the coulombs per meter times meter. So over here I could say this is lambda ds, the arc length of this little portion, which then I could say is lambda times r d theta, because that's what arc length is. It's radius times angle. And then, so why don't I just put that in for now? Lambda r d theta over r squared. So there's my expression for E, or dE, times the cosine of the angle. All right, now you see, I've got a d theta here, I've got a theta, a cos theta, I could integrate that. But before I do that, we first need to figure out our limits. So if this whole arc is 120 degrees, or 2 pi over 3, then starting at theta 0 here, according to here, theta 0 when we're lined up with this point, this must be that divided by 2. And this is down that same angle of 60 degrees. So those are my limits, from minus pi over 3 to positive pi over 3. Furthermore, we can plug in the lambda from the previous part of the problem. That was 3q over 2 pi r. Okay? So, I'll take all the constants out. K, 3q over 2 pi r, r over r squared. So that's all of these. And then the cos d theta integrates to sine. And my limits. All right, so I've integrated. Now I've got to plug in the limits. Okay. I'll touch up the constants in the front. So that'll be the r here and the r here. And what I have is 3kq over 2 pi r squared. And then I plug in sine of positive pi over 3 minus sine of negative pi over 3. Pi over 3 is like 60 degrees, and the sine of that is radical 3 over 2 minus a negative radical 3 over 2. So in the brackets here, I just have radical 3. And so I have the electric field caused by that arc, 3 radical 3 kq over 2 pi r squared. Okay, so there it is. All right, I'll pause to give you an opportunity to jot this down. Okay, couple points. We're going to be calculating formulas for electric field for a lot of charge distributions, and it's very easy to make a mistake somewhere along in these long proofs. So what I recommend is to always, when you're all done, compare your formula to the basic formula for electric field. You always need a K in the formula, and then you need coulombs over meters squared. And if we look here, we've got these numbers don't have units, right? So we've got units for K, we've got coulombs on the top, and we've got meters squared on the bottom. So the formula appears to be correct. If we had something like this because we made a mistake somewhere in our calculations, we would say, oh wait, we got meters cubed in the bottom, the formula's not right. And we'd go back and look for mistakes. So very often it shows you errors, that little check, and then you could go back and try and find those errors. If we lost the radical 3, this technique would not help us with that because the numbers don't have units, so it won't detect that we're missing a number in there. All right, so that's one point. And the other point, I just want to summarize. What we did is I had to erase it because I needed room. We had the arc. We imagined this little piece here, and then we figured out the dE, and then we multiplied by cos theta, and we integrated all these dE in the x direction, added them up for the whole bar, and that's the answer we got, which is the net electric field for that arc. Okay? So I don't remember if, yeah, I think I already paused to give you an opportunity to jot this down. All right, let's take a look at another example. So, suppose we have an arc like this, which is 120 degrees, which would take us 90 here, and 120 is like that maybe. And this is plus Q and R and the same angle. And then over here, I'm going to have another 120 degree arc. And this is going to be minus Q, R. And we want to find the net electric field right there in the middle. Rather than redo the integration, we could use this formula that we already derived. We know that if we go 120 degrees and we go 60, which is the midpoint, the net electric field caused by this positive arc will point like this. I'll put E for the positive part. And it has this value. This piece also has the same value of electric field, but because this arc is negative, rather than pointing away from that center point right here, it's going to point toward that center point because of the negative charge, right? So we have like this. Oops. Those arrows are the same length. To find the net electric field, we have to add these as vectors. And if you look closely at the diagram, you would see that the x part this time goes away. These are going to have the same x part. But the two y parts are going to add. Okay? So we can therefore say E net is equal to 2 times the y component of each of those arrows, which will be, if I go like this, right here, theta, then I can use the cosine function. Now, I don't want to erase this because I'm going to need it. So I'll go underneath it. So expanding that to the E of one of those arrows, which is here. Times the cosine of that angle. Well, if this is 60 degrees, as we said, then this is 30 degrees, the other part of 90. And therefore, this is 30 and that's 30. So we know that angle's 30 degrees. So we could say cosine of 30 2 times the length of one arrow times cos to pick the y component, doubling it because we got 2 y components. And the cos of 30 is radical 3 over 2. We can put that in and touch things up, but I'm not going to bother because those are just details and you could work those out on your own if you wanted to. So again, you can use formulas recycled and then just use vector addition as we did with protons and electrons. So there's our first sort of exploration of charge spread out along objects. We looked at the charge by an arc like this, and what we do is we imagine a little slice of it, and we use kq over r squared over there, and then integrate to find the net electric field caused by all the pieces in the right direction. Okay? So that's it for today. I'll see you in the next physics video.